Welcome all. Today we will discuss Noetherian modules. So first we will prove a theorem which gives three equivalent conditions to define Noetherian modules. And then we will see many examples of Noetherian modules and non-Noetherian modules. And at the end we will see some properties of Noetherian modules. So here is the theorem which gives three equivalent conditions to define Noetherian modules. So what is Noetherian module? It is just something more than finite generation. So this is just class of finitely generated modules, even something more than that. So you consider an R module M, then this theorem is saying the following three conditions are equivalent. First one is ascending chain condition. What is that? So if you consider an ascending chain, by ascending chain I mean this kind of chain, M1 is contained in M2, so on. So this chain, it is indexed by natural numbers and it is increasing chain. So this ascending chain of submodules of M, that should be stationary, and by stationary I mean there should be some point n0 or certain stage such that after that stage or after that point n0 all the modules M sub n are equal. And second statement is saying that module M, it satisfies the maximum condition. And what is that? So by maximum condition we mean that if you consider every non-empty family of submodules of M, then that family has a maximal element. So in general, for arbitrary module M, this condition may not be there. So if you consider a non-empty family of submodules, it may not have maximal element. But if we have this condition, then we will prove that we have all these three conditions. And third one is saying that it satisfies finiteness condition. And what is that? So it is something more than finite generation. So here it is saying that not only M is finitely generated, but every submodule of M is finitely generated. So if every submodule of M is finitely generated, then in particular, since M itself is a submodule of M, then M is finitely generated. And in fact, this is something more than that. So let's prove this theorem. So first we will prove that if M satisfies this condition, then M satisfies this condition. So let's assume this condition, and then we will prove that M satisfies this condition. So to prove this second condition, first we assume or we consider a non-empty family of submodules. Let's say this is our non-empty family of submodules, and we prove that this family, it has a maximal element. So we prove this implication by counterpositive way. So if possible, we assume that F does not have a maximal element, then we will prove that then such M that does not satisfy this condition. So we will try to produce a non-stationary ascending chain, or I mean infinite ascending chain which is not stationary. So how to do that? So since this family is non-empty, we have at least one module in this family. This is not maximal. Since we have assumed that F does not have a maximal element, in particular this is not a maximal element of F, so therefore there exists some M alpha 2, something bigger than M alpha 1 in this family. And next we consider this one. So since this element, it is also there in F, and we have assumed that F does not have a maximal element, so in particular this is also not a maximal element of this family. So in this way there should be something bigger than M alpha 2. Let's say it is M alpha 3. So in this way, inductively we can produce a non-stationary ascending chain like this. And why it is non-stationary? Because at each point this containment is strict containment. So it is this is ascending chain and it would not be a stationary chain. So therefore M does not satisfy this condition. So this contradicts this assumption that F does not have a maximal element. So this is the contrapositive way. We want to prove 1 implies 2. So we have assumed that suppose 2 does not hold true, then we are proving that M does not satisfy the condition 1. So this is the contrapositive way. So this thing proves the condition 1 implies condition 2. And next we will prove condition 2 implies condition 3. So here is the proof. So second condition, it is saying that M satisfy maximum condition. What is that? That every family, non-empty family of submodules of M has a maximal element. That is maximum condition. And we want to prove, so assuming this condition, we want to prove finiteness condition. So to prove finiteness condition, what we do? We just consider a submodule of M. Let's say it is N. And we want to prove that this N, it is finitely generated. How we can prove that? So we have to use this condition. For that we have to consider a suitable non-empty family of submodules. So here is that suitable non-empty family of submodules. So let A be the family of all finitely generated submodules of N. So here A, this is the family of all finitely generated submodules of M that is contained in N. So question is this family non-empty? Yes, it is non-empty because this trivial submodule 0, it is there, because 0 that is contained in N and this is finitely generated. So this family, it is non-empty. Then by the given condition, this family, it has a maximal element, let's say N prime. And next, it is enough to show that N prime is same as N. Because see, N prime is a maximal element of A. So in particular, N prime is there in A, therefore it is finitely generated submodule of N. Once we prove that N is same as N prime, then N is also finitely generated. So let's prove this thing again by contrapositive way. So if possible, let N prime, it is strictly contained in N. So then there exists X and an element in N but not in N prime. Then what we do, we just consider this submodule. So this N prime, it is already finitely generated and we are adding one more element in that generating set. Then this submodule, that is also finitely generated and it is contained in N. Why? Because X is there in N and N prime, that is also there in N. So this submodule, it is contained in N and this submodule, it strictly contains N prime. Because X is there in this submodule but X is not there in N prime. So this is finitely generated submodule of N which strictly contains N prime, and this is a contradiction. This contradicts the assumption. This contradicts the fact that N prime, this is a maximal element of A, and this contradicts the assumption that N prime is strictly contained in N. So therefore, N prime is same as N, and hence N is finitely generated because N prime is finitely generated. So this proves 2 implies 3. So maximum condition, that implies finiteness condition, and it remains to prove that finiteness condition, if M satisfies finiteness condition, then M satisfies ascending chain condition. So to prove this condition, we consider an ascending chain, and we just have to prove that this chain, it will be stationary, it will stabilize somewhere. We have this condition. So how to use this condition? Considering this ascending chain, we can have a submodule, let N, that is union of Mi, I greater than or equal to 1. So in general, union of two submodules need not be a submodule, but if there is a containment relation like this, then if we take their union, one can prove that this is also submodule of M. So this is a submodule of M, and then we can use this condition. Since we have this condition and this is a submodule of M, so then N, that should be finitely generated. Let's say it is generated by x1 up to xn for some xi belongs to N, So we just have to find certain point n naught such that from n naught onwards all the modules are same. So how to do that? So we will use this fact. So this union is generated by this x1 up to xn. So if we consider each xi in this generating set, then it will be contained in, so I should write it is xj, then it will be contained in m sub ij for some I sub j. And then if we take the maximum of I1, I2, In, then xj, it will be contained in mn naught for all 1 less than or equal to j less than or equal to n. So using this, that this union it is generated by this. So if we consider each element in the generating set, since it is there in the union, so xj that will be there in at least one submodule from this chain. So let's say it is m sub ij, and then if we take the maximum of these indices, let's say it is n naught. So we have considered this ascending chain. So if index is bigger, then that module is also bigger. So this index n naught, it is bigger than each index I1, I2 up to In. So m sub ij, it will be contained in mn naught. So therefore this submodule, it contains all elements in this generating set, and thus n, it is contained in mn naught. And we claim that from n naught onwards all the submodules are same. How to prove that? So if we consider m greater than or equal to n naught, then we already have this relation, n is contained in mn naught. But if we consider bigger index m, that is greater than or equal to n naught, then mn naught, it is contained in m sub m, because we have considered this ascending chain, and everything is happening inside this union. So this m sub m, it is contained in n. So we have started with n and ending with n, so we should have equality at each step. So we should have equality. So this implies that mn naught, it is same as mm sub m. So we have proved that this ascending chain, it should be stationary. Thus we have these three equivalent conditions, that if m satisfies one condition, then it will satisfy all the conditions. Okay. So an R module M satisfying any of the equivalent conditions, this ascending chain condition, maximum condition, and finiteness condition, is called a Noetherian R module. Okay. So here are some examples. A module having only finitely many submodules is Noetherian. So let's see first that what are the modules which has only finitely many submodules. So if we consider a simple module, let's say it is M, then how many submodules we have? Only two. One is this 0 and another one is whole thing. So simple modules have only finitely many submodules. And if you consider a finite abelian group, so each abelian group you can think it as a Z module. So if you consider a finite abelian group, if you consider this as a Z module, is it Noetherian? So again we can have this thing. So we can see that if you consider a finite abelian group, then it has only finitely many subsets, and hence it can have only finitely many subgroups. So here subgroups are just here subgroups will give the submodules, Z submodules. So since any finite abelian groups has only finitely many subgroups, so if you consider it as a Z module, it has only finitely many submodules. So it is satisfying this condition. Now why a module having only finitely many condition is Noetherian? So we should verify at least one of these equivalent condition. So in this case we can see this condition easily, because your module M has only finitely many submodules. So you cannot have infinite ascending chain, infinite non-stationary ascending chain, because you have only finitely many submodules. And you can verify other conditions also. But we have already proved that these three conditions are equivalent. So since it is satisfying this condition, so this a module having only finitely many submodules, it is Noetherian. Here is another example. If you consider a finite dimensional vector space, I claim that that is Noetherian. Why? Because if you consider V, that is finite dimensional vector space over a field K, then of course it is finitely generated as a K module. Now question is it Noetherian? So to prove that it is Noetherian, we can verify finiteness condition. What is that? That if we consider every submodule, so in this case every submodule of V, it is just subspace of V. Now question is this submodule finitely generated? So if you consider a finite dimensional vector space, then its subspace that is also finite dimensional, therefore its subspace that is also finitely generated. And hence this V, it satisfies that finiteness condition, therefore it is Noetherian. Now what about infinite dimensional vector space? So if you consider W, so infinite dimensional vector space over K, then is it Noetherian? So answer is no, because this W it does not satisfy that finiteness condition. And here in fact this W, it is not finitely generated. So Noetherianness, it is something more than finite generation. So every submodule is finitely generated. So if you just forget about every submodule, here W itself is not finitely generated. So therefore it is not Noetherian. And you can verify other three conditions also. So for example, you can have a non-stationary ascending chain of submodules of W. So for example, if it is generated by, or if it is a basis, let's say W1, W2, so on, Wn, so on, infinite set, then you can produce this, you can consider this non-stationary ascending chain. So you consider the subspace generated by W1 up to Wn. Then W1, it is strictly contained in W2, it is strictly contained in W3, so on. You can have infinite non-stationary ascending chain. So in that way also you can say that this W, it is not Noetherian. Here is another example. So if you consider a cyclic group, again it is abelian group. So you can think it as a Z module. So this Z module, is it Noetherian? So answer is yes, it is Noetherian. Why? Because we can verify that finiteness condition again. So if you consider a submodule of this, Z submodule of this, what is that? It is a subgroup of this cyclic group. And any subgroup of a cyclic group, again that is cyclic, and therefore it is finitely generated. And by cyclic we mean that it is generated by a single element. So since any subgroup of a cyclic group, it is again cyclic, so therefore it is finitely generated. So every cyclic group is Noetherian Z module. So what about Z as a Z module? It is also cyclic. It is generated by, so Z, it is generated by 1. It is additive cyclic abelian group. So it is Z module, and it is Noetherian. Or you can just think, you can directly verify this. So every submodule, Z submodule of Z, how does it look like? It is just additive subgroup of Z. And every additive subgroup of Z, it looks like n times Z, and it is generated by n. So every subgroup is finitely generated. Therefore every submodule of Z, that is also finitely generated. And you can verify other conditions also. For example, this is good exercise to verify that you cannot have infinite non-stationary ascending chain of submodules of Z. Okay. So Z as a Z module, it is Noetherian. And here is one example which is not Noetherian module, but it is finitely generated module. So you consider the polynomial ring in infinitely many variables over a field K, And then you can think this R as a module over itself. Then if you think this R as a module over itself, it is finitely generated because it has identity element, and this R, it is as an R module, it is generated by 1. So it is finitely generated. But question is it Noetherian? Answer is no, because you can consider this ideal. So in this case, you are considering module R over itself. So submodule of R, it looks like just ideal. So these are just ideals of R. So if you consider this ideal generated by all the variables, then it is not finitely generated. So this is submodule. So it is not finitely generated submodule. One can verify that this is not finitely generated. Why? Because if it is finitely generated, then you will have some finite generating set, let's say f sub m. And if you consider each polynomial in this generating set, only finitely many variables are involved. So if you consider this whole generating set, only finitely many variables are involved. Let's say from x1 up to x r, okay, x sub r. Then if you consider x sub r plus 1, then you cannot write x sub r plus 1 as a linear combination of this thing, because so each polynomial, it is there in this ideal, so its constant term is 0. So if you substitute x1 up to xr, all are 0. If you substitute that in f1, then you will get 0. So suppose you have an R linear combination of you can write x sub r plus 1 as R linear combination of this generating set. Then you just substitute x1 equal to 0 up to xr equal to 0. Then in one side you will get x sub r plus 1, and in the right hand side you will get 0. So that will give a contradiction. So you can verify that this is not finitely generated, and therefore so you can have a submodule of R which is not finitely generated. Therefore as an R module, it is not Noetherian, because you have a submodule which is not finitely generated. And you can verify other conditions also. So if you consider this ideal generated by x1 up to x sub I, so these finitely many variables x1 x2 up to xi, then you can have this ascending chain, non-stationary infinite ascending chain. So in that way also you can say that this R module, this module over itself, it is not satisfying that ascending chain condition. So it is not Noetherian. And here is one proposition. So it is saying that how Noetherianness behaves on a short exact sequence. So you consider this short exact sequence. So then this proposition is saying that this middle one, so this is short exact sequence of R modules. Then this is saying that this middle one is Noetherian if and only if these two modules are Noetherian. So in terms of submodules, we can prove that this thing. So you consider a submodule of an R module M, then you can have this short exact sequence M mod n to 0. So then this statement, it is saying that this M is Noetherian if and only if this submodule n is Noetherian and this corresponding quotient module, that is Noetherian. So how to verify that? So we have written here, it is enough to prove the particular case only, this case only. And this is just particular case of this one, because of this we can consider this short exact sequence. And why it is enough to prove, or it is enough to verify this particular case only? Because if you have this short exact sequence, then this first one, it is isomorphic to its image here, and this image, it is submodule of M2. So M1 is Noetherian if and only if this is Noetherian. And this quotient module, so by first isomorphism theorem, you can have that M3, it is isomorphic to M2 modulo kernel psi, and kernel psi it is same as image phi. So therefore M modulo image of phi it is isomorphic to M3. So M3 is Noetherian if and only if this quotient module is Noetherian. So if we have this particular case, using that we can have this general case because of these isomorphisms. So let's prove this particular case. So first we will prove these implications. So let M be a Noetherian M be a Noetherian R module, and we want to prove that this submodule N and the corresponding quotient module, these are Noetherian. So we just have to analyze the submodules of N and this quotient module. So how does it look like, a submodule of N? So a submodule of N, this is also a submodule of M, and since M is Noetherian, every submodule of M is finally generated. Therefore every submodule of N, that is also finally generated. So you can verify it directly. So N is Noetherian in this way. And what about this quotient module? So every submodule of this quotient module, it looks like P modulo N for some submodule P of M which contains N. So if M is Noetherian, then this P is finally generated, and hence this quotient module P mod N, that is also finally generated, because if P is generated by, let's say, x1 up to xn, then P modulo N, it is generated by these equivalence classes of x1 up to xn. So therefore M is Noetherian, that implies that its submodule N and the corresponding quotient module are Noetherian modules. And next we prove the reverse implication. So suppose this you consider a submodule of M, suppose that submodule is Noetherian and the corresponding quotient module is Noetherian. So we want to verify that M is Noetherian. So to verify that, we will verify that finiteness condition. For that we consider a submodule of M, let's say it is L, and then we want to prove that L is finally generated. So we have these two conditions. So considering this submodule, how can we use this condition? Okay. So considering this submodule, we can have two submodules. One is submodule of N, another one is submodule of M mod N. So what is that? So L is a submodule of M. So L need not be a submodule of N, but if we consider this intersection, this is a submodule of N. Okay. And so again, you cannot directly consider L mod N always, because L need not be a submodule of L, but if you consider L plus N, then this is a submodule of M which contains N. So therefore you can consider this quotient module. So considering this submodule of M, naturally we have these two submodules. One is submodule of N, another one is submodule of M mod N. So since N and M mod N are Noetherian modules, this is finally generated, and this module, that is also finally generated. So using this finite generation, we just want to prove that L is finally generated. How to do that? So this is just observation. It follows from the second isomorphism theorem that this quotient module, it is isomorphic to L modulo this intersection. So using this isomorphism, now we have that L intersection N is finally generated R module, and this quotient module, that is also finally generated. So this is exercise. One can verify that finite generation of this and this, it proves that L is finally generated. So if we consider a short exact sequence, then these two are finally generated. That implies that middle one is finally generated. One can verify that. I will leave this thing as exercise. So here is the corollary. So here this corollary, it says that how Noetherianness behaves when we consider direct sum, or when we consider usual sum. So it is saying that if you consider Noetherian R modules, let's say M1, M2, M sub n, these are Noetherian R modules, then if you consider their direct sum, then that is also Noetherian R module. And how to verify that? So using that previous proposition, we can prove this, and we will use induction on n. So if n is equal to 1, then it is just M sub 1, and that is Noetherian R module. It is given condition. So if n is 2, then we have these two direct sum of two Noetherian modules. In that case, we can just consider this short exact sequence. So here this map is given by, this is natural embedding. So x is going to x comma 0 and x comma y. So this map is given by projection map on the second component. So one can have this short exact sequence, one can verify that this gives a short exact sequence, and we have verified or we have proved that middle one is Noetherian if and only if these two are Noetherian. So if M1 and M2 are Noetherian, that proves that this direct sum is Noetherian. And then so if n is 2, then this is Noetherian, and in general we can consider this short exact sequence. So suppose you are considering this n many Noetherian R modules, then you can consider this direct sum, and you can split this into direct sum of this and this. So by induction hypothesis, this is Noetherian, and this is given condition M sub n is Noetherian. Therefore this direct sum, that is this one, that is also Noetherian. So using previous proposition, we have this statement, and using this statement, next we prove this one. So we have verified that if you consider some finitely many Noetherian R modules, then their direct sum is also Noetherian. But what about usual sum? In that case, you have to consider Noetherian submodules of an R module. So here M is an arbitrary R module. It need not be Noetherian. Okay, you don't know whether it is Noetherian or not. It is just arbitrary R module, and you have considered Noetherian submodules. So by Noetherian submodules, I mean that so n sub 1 in particular, this is an R module, and as an R module it is Noetherian. So it satisfies that finiteness condition or all the equivalent conditions. So if you have these Noetherian submodules of an arbitrary module M and you take their usual sum, then that is also Noetherian. Okay, how to verify that? So you can think this as R module. So as R module, it is Noetherian. So if you consider their direct sum, then this R module, it is Noetherian. From this direct sum to usual sum, one can have this natural projection map. What is that? So here elements are look like this n tuples, where ith component is coming from n sub I, and then one can map this n tuple to this usual sum x1 plus x2 plus xn, because everything is submodule of M and everything is happening inside M. So one can consider this usual sum, and then one can verify that this map, it preserves addition and scalar multiplication, and therefore this is an R module homomorphism, and one can verify that this is surjective R module homomorphism. Why? Because any element in this usual sum, it looks like this. So this is surjective R module homomorphism, and then one can so then this one, it is just isomorphic to the quotient module of this direct sum, and because of this proposition that if something is Noetherian, then its quotient module, that is also Noetherian. So using that, since this direct sum is Noetherian, so quotient module of this, that is Noetherian, and that quotient module, it is isomorphic to this usual sum, that will also be Noetherian.